So we'll start fairly easy with the talks and go straight into category theory. You may have heard of category theory before. It is the most abstract type of maths that I think there is, to be honest. And basically what they do in category theory is describe the behavior of how things work instead of how they're implemented, which as programmers, obviously that's the kind of thing we like because, you know, then you're not bogged down in the details of how you're implementing stuff. And it just so happens that types and functions in Scala form a category. And what that means is that we get all this sort of amazing free, all this amazing functionality from the maths that allows us to do some crazy stuff in Scala. And it's the theory behind libraries like cats and Scala Z. So you get all these kind of scary, you know, crazy words coming out of category theory, like functors, applicatives, monads. You know, you may have heard of some of this before. And it really, you can go absolutely out there. And you may have seen some talks by crazy people doing this stuff before. But what I'm going to do is not even like tell you why this stuff is useful for particularly, because hopefully you'll know that already when I talk about it. But what I'm going to do is just basically define what these things mean in terms of things that you've already seen before in Scala and when you're doing programming. So if we get started with a functor, so probably some of you have heard of this one before, but basically all you want to know, or the very basics of what you want to know about a functor is that it is something with a map function. And, you know, you're all Scala developers, you've all seen this stuff before, so you know why map is useful. And you have all these examples like list and future and option, either, and this strange validated thing that maybe we'll talk about later. But also it's interesting to note that a tuple, so say a tuple of A and T actually has a map function on it. You just sort of map on the right. And in libraries like cats, you can map over a tuple, and sometimes that actually comes in useful. And all of these concepts, they kind of have these laws that sort of explain mathematically actually how a map function is supposed to work. And so in this case, a functor has these laws of identity and associativity. So identity just means if you map over the function that doesn't do anything, then you get the same thing back, which I hope you'd agree, if you have used a map function before, if you had a map function that didn't have that property, it'd be pretty strange, to be honest. And associativity basically just means that if you map over some function and then you map over a different function, then that's the same as mapping over the combination of those two functions. And again, you kind of intuitively know that these things, how a map function should behave, right? And so for the next ones, I'm not even going to talk about this stuff because you have the intuition there already. So maybe this next one is a bit more unfamiliar. So this is an applicative, and all applicatives are functors, but actually the converse doesn't hold. So not all functors are applicative, and you see that now we can't have an applicative for a tuple like before. But so what an applicative is you just have, well, firstly, you have a pure function, so it allows you to just wrap up some element in your sort of type constructor to make it an applicative. So, for example, you can call list of one and you get a list. You can call future successful and you get a future, right? So all of these things are applicatives like that. And it has one other thing that you need for it to be an applicative, and this is... So there's actually lots of equivalent formulations, but the one I actually find most intuitive is this map2 thing. So if you have this map2, it's basically being able to zip and then map over it. So if you've used a zip before, you can say zip two futures together, and you get a future of the tuple of their elements. And yeah, so if you can zip and you can wrap something, then you get an applicative. And say a monad, hopefully a lot of you have heard this already, but it's basically just something with a flat map, more or less. And Again, it's an applicative as well, so it has a pure function too. And whereas with an applicative, you have to, it's more about doing things in parallel. A monad, you can do things sequentially and depend on the previous answer, and that's kind of the difference between them. But otherwise, you know what a monad is, you know what a flat map is, you know. Okay, so maybe, again, this one getting a bit more out there. So what is a Kleisli? So a Kleisli is basically just an A to M of B. So the M here has to be a monad, so it has some flat map, it has a way of flattening. But basically, you just think of it as an A to M of B. And you use these things all the time, because every time you do a flat map, the argument is an A to M of B, right? And there's a few things you can do with Kleislis, and actually it gets a bit complicated, but I think one of the most underappreciated things about them is just to compose them. So you can think of them as like monadic functions, basically. So let's say you have an A to M of B and a B to M of C. Then you can compose them and you make an A to M of C. And the way to do that, so you take your A, map it to an M of B, then you map the B within your M to another M of C. So you have an A to M of C. And then the M's you can flatten because the M's are a monad, right? And then that gives you an A to M of C. So basically, if you want to build up, say, a pipeline of maybe futures, you can just compose monadic functions and you just get you get a function that takes an input and returns a future at the end. And you don't have to worry about all the flat maps in the end because you just compose them. Okay, next one, natural transformation. So yeah, this is sometimes called function K. I think that's what they call it in CATS. But mathematicians call it a natural transformation. But basically all it is an f of x to g of x. And again, you use these things all the time. So things like head option, that is a natural transformation from a list to an option. And to list is a natural transformation to a list. And even this await, you can kind of think of as a natural transformation from a future to the identity monad. Okay, if you didn't understand that, don't worry. Okay, and now a monoid. So a monoid has two things. It has a combine operation and an identity element. So your combine operation, it basically just takes two elements, combines it into a single one. So for example, the integers under addition. So you can take two integers, add them together, you get a new integer, right? And then the combine operation has to be what's called associative, and all that means is that you don't need to worry about brackets, right? It's just, you don't need to care, it's fine. And you need an identity element. And so in this case, it's 0. So if you add 0 to anything, then you don't change that thing, basically. That's all that it means to be an identity element. Okay, so do we really know category theory? So a monad is a monoid in the category of endofunctors. What the hell does that mean? So an endofunctor is, don't worry too much, basically. It's a functor to the same category, right? And if you think about how I defined functors before, it was really a functor from the category of types to the category of types. So actually, every functor that you usually think about when you think about programming, Scala, all of this is an endofunctor. So we're just going to consider the category of functors. Now, in the category of types and functions, you need a combine and identity with these signatures to be a monoid. Sorry, a monad. Monoid. But in the category of functors, you then have this sort of situation going on. So what happens is you need to be able to merge two type constructors into a single one, right? In the same way that on the left here, we're combining two elements into another element, We need to merge two type constructors into another type constructor. And for an identity, we need a way of wrapping something that doesn't affect this sort of merging property that we've talked about before. And what are these things? Well, we need a way of flattening, that's a flat map. And we need a way of wrapping, that's a pure. And that's exactly what you need to be a monad. Okay, that's it, thanks.